Hi, friends. I'm here to demonstrate an interactive section of what I posted on my page on how do I explain electromagnetic induction to students. I want to make use of interactive simulation, as this is more of practical and more of interactive and friendly. So, and uh, just follow me. I want to ask you a question, or some questions. Have you ever wondered how electricity is generated, is distributed to our homes, or a fuel dispenser dispense fuel to car, cars, lorries, how a bicycle dynamo works? Have you ever wondered about that? So, don't worry. Here you will get to know what all these things, what principle they make use of. So there's something what is called electromagnetic induction. From the word electromagnetic, this is just a magnet producing electricity. That is what we mean by electromagnetic. That is, we get our electricity from magnet, and this is discovered by Michael Faraday. So there were two scientists and Joseph Eric. So now this is what is going to happen. We need three components, or let me say elements, to demonstrate this electromagnetic induction. Induction has to do with induction, that is, you induce, you make things to happen by something. Okay, so making things happen. Now we have a bar magnet. A bar magnet is surrounded by a magnetic field. We know that one. And we have a coil of wire. We have this one will serve as a galvanometer. Okay, for us, we don't have a galvanometer per se, but this one we use it as a galvanometer. So that's the three things that we need. And also we have another indicator where I will show us later, and that is the bulb. So now let's start now. So now, for electromagnetic induction to happen, there must be a relative motion between the bar magnets and the coil of wire. What might be relative motion? That there must be the bar magnet. The magnet must be moving. Why the stage coil stays, or the coil must be moving while the bar magnet stays. While the magnet stays. So now, as there is movement of this bar magnet, this is causing a change in magnetic flux. Okay, change in magnetic flux as this thing in turns produces what is called currents, induced currents inside the coil. As you can see that now, when the bar magnet stops, no current. If you look at the deflection of this galvanometer, you can see that no deflection. But when you move the bar magnet, there is what deflection, telling you that there is current. Current is induced in the wire. So when you move it, you can see move it like this. The same thing applicable when you take coil and when you move it, there is what deflection of the current. That is, current is induced. So what is that? Is what we say magnetic. Changing magnetic field produces what we see as electricity today. So now, if I change this indicator, and let's see what will happen if I move this bar magnet. Can you see now? Current is supplied to the bulb in this current. You can see now as I move it, there is what? There is light. There is electricity. So for electromagnetic induction, there must be a change in magnetic flux. Okay, There must be a what change in what in the magnetic flux. And then moreover, magnetic flux depends on the it depends on the magnetic field, depends on the area of the surface, and then it also depends on the angle between the field and and the normal. So that one is another case entirely. But yeah, I just want to explain what I mean by electromagnetic induction. So now, if I want to define the electromagnetic induction now, I will say electromagnetic induction is the process whereby electricity is, induced EMF or induced current is produced, okay, due to the change in magnetic flux that leaked it, okay. The production of induced current or EMF due to the what change in the magnetic flux in the coil, okay, in the coil or in the conductor. So that is what I mean by electromagnetic induction. So if one let us talk about the direction of the current. If you look at the direction of the current, that is the deflection, you see that it's always in opposite direction to the cause that changes it. So, and what is that cause? I mean, what is that change? So the change that causes it. So that is electron. That is magnetic. Change in magnetic flux. So change in magnetic flux is the is always in opposite direction to the induced current, and that one is given by Lenz. So we call it refer to as Lenz law. Okay, so the Lenz law states that the direction of the induced current in a wire, in a coil of wire, is opposite to the change that causes it. So what does that mean? Electromagnetic change. So you can see now, as I move the bar magnet, the north side to the right, what happens uh to the direction of the coin, the deflection? The deflection moves to the left. Can you see this one? Right, left. Okay, you can see that is in opposite direction. So that one explains the Lenz's law. And what other things I can mention here? That is, if I want to add it more, what are those factors that have that this in this current could depend upon? That is, uh, this in this current, the production of the in this current, it depends on the number of turns of wire. This is two. I can increase it. If I increase it, there will be larger currents. Okay, let me make use of this indicator for this. Let me use of this. You can see the brightness of the bulb. Let me increase it. Can you see? Can you see that it's brighter than the when it's we have it on? You can see something before I move on. By the time I increase this, okay, no, by the time I did not take this, I did not move the bar magnet. There is there is current. That is either the coil is moving or the bar magnet is moving or the magnet is moving. Okay, so either the two. So there will be production of electricity, and this is what is make use we make use in electric power generation. Yeah, in power station.